All right, folks. So this is all kind of weird because you've just obviously taken a test on the gas laws. And yet, what I want to do is sort of give some last few wrap up ideas about gases that will somewhat connect to what we're going to be talking about in the last couple of days of the term here, an area called condensed states of matter. So this concept of the gas laws, there were three things that I want to make sure that I talk to you guys about. The first is a common mistake that students make. So you would see a question just like this. What is the volume of 752 grams of neon gas at 1.22 atmospheres and negative 15.2 degrees C? Now, for most of you, this is not going to be too much of a problem. I think you would look at this and say, all right, well, I'm going to go ahead and use the ideal gas law to solve this. And that's because you just worked with the ideal gas law. But keep in mind that it wasn't that long ago that whenever you saw a volume of a gas, that triggered in your mind that you needed to use the concept or the idea of 22.4 liters of any gas is 1 mole of that gas at STP. Hold on. Oh, Lumpy, I'm right here. How did the door get shut? How did the door get shut on you? That's weird. Sorry, I just had to let my son into the door. It's freezing, isn't it, Knucklehead? It's cold. Okay. And so, in fact, let me just recast this question to make it look like one of those old questions. So there you have it. That's actually when you have 1 atmosphere and 0 degrees C, that's STP. So I could have written just plain at STP, but I decided to make it look a little bit more like the previous question. And of course, you'd approach these two questions in very different ways. STP, though, is really the key area to something. It's the sort of flag that I want you to make sure you're paying attention to, because if you immediately recognize in the second question, let's just call this, for argument's sake, we're going to call this one A, and we're going to call this question B, okay? So if you looked at B, the first thing that should trigger in your mind when you see 1 atmosphere and 0 degrees C is STP. And then it's totally fine. In fact, it's preferable that you go ahead and use the 22.4 liters per mole equivalency. All right, it's vital because it makes it a heck of a lot more efficient for you to approach this problem in that way. But you do have to be incredibly alert to the fact that in question letter A, you don't have STP going on there, so you cannot use the 22.4 liter equivalencies. Okay, so be efficient. Use the 22.4 liter thing when you can, but make sure you avoid it like the plague and use the ideal gas law when it doesn't make sense to, because you don't have the standard temperature and pressure conditions. All right. Okay, item number 2 is something that I wanted you guys ideally to understand before you took this test, but of course we ran out of time. I needed to have the test on Friday, so if I had been able to have the test on Tuesday, you would have had this on your test. And that is the Graham's law of effusion. Now, Graham's law of effusion can be a pretty complex thing, but I'm going to enormously simplify it. And in fact, I'm going to apply it to something that I think that we're all fairly familiar with. The concept of why is it that helium balloons seem to only last for about a day? And I'm talking about the latex ones, not the mylar ones that we have, but the ones that are just the traditional old school latex ones. They're floating with helium, for your birthday party, and then by the end of the evening, oftentimes they're at the bottom of the floor, and in fact they're much smaller. As opposed to if you had a balloon that you pumped up with your own lung power and tied up the thing and tossed it around your room, those things would last for weeks, pumped up pretty large, and they would stay big and happy until your mom got sick of seeing them, and then she'd pop them with a pin and throw them away. Yeah, what's up, Lumpy? What do you see? I don't know. Tell me what you see. Oh, I know. I got to clean that whole thing. Cal just pointed out to me that the fish tank is a mess, so I have to work on that later after doing this screencast. All right. So again, we want to know why it is that helium balloons seem to deflate so fast, as opposed to this exact same balloon in terms of the latex balloon itself. If I were to pump it up with my own air from my lungs, it would actually stay relatively large for a much longer period of time. So let's first, before I get into that, let me first explain this concept of effusion. Effusion is the movement of gas through a small hole. Now that sounds really bizarre, so let me show. Okay, so what we have here is I want you to imagine that this, what I'm showing right here, is a balloon, okay? And we're zooming right in on the balloon, so we're only seeing a very small part of the portion of the balloon here. And this is the inside of the balloon, and this would be the outside of the balloon. What you may or may not realize is that the latex, while it seems like it's totally airtight, actually has tiny little pores in it that do allow gases to get out. And so what I'm showing here with this opening here, this is one of those small little pores or holes through which a gas could actually leak if it wanted to, especially if the pressure in here was greater than the pressure out here. There'd be a lot of opportunity for a gas particle to bounce around in such a way and be able to get enough energy to pop through that little hole that we got going on here. So over time, I don't think it's too much of a surprise for you to imagine that this particle could jet out and be lost, and it's not going to go back in to the higher pressure area of the balloon. It's going to stay out there and be lost essentially into the environment surrounding the balloon. And after a period of time, a lot of these guys are going to be leaving until you're left with actually very few of the gas particles still hanging out inside. And in fact, at some point, the pressure inside the balloon is going to be the same as the pressure outside of the balloon, and therefore there's not going to be any net loss of particles into or out of the balloon. But you understand the concept here. Effusion is the movement of these gas particles as they escape through a particular hole. Now, what Graham's law of effusion stated here, which is a pretty simplistic thing on its surface, but is actually incredibly complex, is that the rate of effusion, so the speed with which a particle leaves one area through a hole and goes out into the environment, is proportional to 1 over the density of the gas. So let me write that out because that's a mouthful. And I also don't want you to forget that we measure density in the same way we always have measured density, which is simply mass over volume. Okay, so that's what density we're talking about. So let's take a look at an example of something here, so it's not so theoretical and crazy for us to wrap our brains around. Let's imagine that we have two gases. We have the gas that makes up 78% of our atmosphere, and so it also makes up roughly 78% of what you breathe out into a balloon when you're inflating a balloon. And we know that for nitrogen gas, it has a molar mass of 28.02 grams per mole. And if we are to look at this let's imagine that we're actually at STP here, okay? And if we're at STP, if we have 1 mole of the N2 gas, then we also know that we have 22.4 liters of that gas. So if we do, that's mass over volume, 28.02 grams over liters. That is going to, if we throw that into our calculator, work out to 0.625 as our density of that particular gas, in this case nitrogen. And then we take something like our helium. And with helium, we have a molar mass of 4 grams, and if I have 4 grams of it and it's at STP, then I would know that I would also have 22.4 liters of that gas within that balloon. And if you do that math, it turns out to be 0.179 grams per liter. So you can see here that the density of helium is going to be quite a bit less than the density of the nitrogen gas. So what does this mean? Well, let me copy this up and transfer it to the next page. Hold on. So I want you to remember, oh shoot, I have to go back here then, that the rate of effusion is proportional to this concept of 1 over the density of the gas. So that means now I have to do the reciprocal of those the densities that I just created. So if I were to do that, if I were to put 1, let's see, I'm going to scooch this down here, 1 over the 0.625 grams per liter that I just generated moments ago, that's going to work out to be 1.60 for my value for N2. Okay, And then if I were to do the same thing, but I did it for the helium, it would be 1 over the 179.179 grams per liter, and that works out to be 5.60 for my helium. Okay? And in fact, let's go back to this again. The rate of the effusion is proportional to 1 over the density of the gas. If it's proportional, that means if the rate of effusion will go up with the increase in this 1 over density index that we just calculated moments ago. So that means the thing that has the higher of the two 1 over density, in this case helium, is going to effuse at a faster rate or leak out of the balloon at a much faster rate than the thing that has the lower 1 over density. In this case, it would be nitrogen. All right, so that explains a phenomenon that you probably didn't care about and I just forced you to care about. Now, the last thing I want to talk to you guys about, and hopefully it'll only take a couple of minutes here, is this idea of ideal. We talk about an ideal gas law, but what is an ideal gas? And in fact, you should know it actually refers to the gas, not to the law, although the ideal gas law is pretty cool. It's referring to ideal gases. And an ideal gas is the way that a gas would normally behave at typical normal pressures and temperatures and volumes. So why is it that we have to make sure that we say that it's an ideal gas? What's the big deal if the gas is at a non-normal pressure or temperature? Well, let's take a look at that and see what we mean. So in an ideal situation, we have gas particles, which are these little pink dots that I'm drawing around here. And those gas particles have a lot of space to move around. Again, this is at relatively low pressures and normal temperatures, so warmish temperatures, say room temperatures. Lots of space. So that means the particles are small relative to the overall volume. So if I were just to sort of close this whole thing in by a fixed volume, you could see that there's a ton of space that exists around all those particles. It's not unlike sort of a golf ball in the middle of Fenway Park. It's not really going to take up much room. It's going to be able to cruise around without too much of an issue there if golf balls could move by their own. So in other words, the importance of this piece is that you can ignore the volume of the particle when there's this much space around. Because don't forget that any one of these particles right here, it does have a diameter, right? There is some volume to it. It's just that they're so far away from their partners, right? They're all over the place like this, that we can largely ignore how big those individual particle sizes are or their volume when we're talking about an ideal gas situation. And so if that's the case, then Avogadro's law works, Boyle's law works, Charles's law works, Dalton's law works, and the ideal gas law also works. But what if we're in a non-ideal situation? And by non-ideal, I mean we have extremely high pressures or extremely low temperatures. And don't forget, those things are very much connected to each other. As we know from Charles's law, you can interchange pressure and volume here because when you decrease the temperature, it also lowers the pressure, or when you decrease, or if you increase the pressure, it also is going to increase the temperature. So they're related. They're very much related to one another here. So if I do one, it's really essentially doing the both it's doing the same thing to both. So we have high pressure, low temperature. Now, if we were to take this same set of particles of gas in a high pressure, low temperature situation, let's just take it from the perspective of the high pressure because that makes it seems to make more intuitive sense. If it's a really high pressure situation, then it's necessarily meaning that you are compressing each one of these particles right next to each other. Right? So you're taking the volume and you're compressing it to a much smaller volume with the same number of particles. Now, here's the problem, is that in this area where we have a tiny amount of volume, so here we just shrunk our volume tremendously now into this little block here, this little cube that I've created here, suddenly the particle volume is significant when compared to the total volume of the vessel in which it sits. So you can't ignore the volume of the particles anymore. So when we talk about the PV equals nRT, that volume is all messed up because of the proximity that they have to each other. And you'd have to, if you were to do this, you'd have to take it into account and it would be a mess and it just wouldn't work out the same way as we can use Avogadro's, Boyle's, Charles, and the ideal gas law to explain how gases work. And the same thing could be said for temperature. If you lower the temperature enough, all the particles are going to start slowing down. They're going to actually start to force the vessel in which they're contained to either shrink if it's a flexible container, or if it's not a flexible container, then you're going to have incredibly low pressure in that situation. I'm sorry, you're going to have incredibly high pressure in that situation because wait, stop. What am I just saying here? If you shrink down the temperature, if you lower the temperature enough, then the molecules or the particles start to come closer to one another, and if you have a fixed volume of something, it's actually going to lower the pressure ridiculously, as you could imagine. And in fact, then the particles, if they start sliding past one another at such an incredibly slow rate of speed, then they start interacting with each other and they have an attraction to each other. And that attraction makes those collisions that these particles might have with a wall inelastic. And so it starts messing everything up. The whole kinetic molecular theory is gone to the birds as a result of having these non-ideal situations. So ultimately, we can only use the ideal gas law in these ideal situations, which is frankly the situations that you typically would find yourself in whenever we're doing these problems. So you don't really have to worry about it too much, but I thought that it's important for you to understand the concept of a non-ideal gas situation. Wow, I went over by a minute and 15 seconds. Bye.